finally time for another USACO walkthrough. Oh my god, I haven't done USACO for like the past whole month. It's crazy. I think I probably did longer. I don't know, you guys tell me when my last USACO video is. But anyways, the point is, I have a little bit of leeway in terms of covering the AP curriculum for Calc and Chem. So, I'm going to throw in a couple of USACO walkthroughs because I did promise I'm going to do open walkthroughs, okay? So, here's the first one. Hello everybody, I'm Karar, and today we're going to be walking through the problem 3 on the US Open Silver. Live solve, it's going to be epic. Hopefully it's a live solve. If I get roasted, that's going to be so sad. Anyways, let's do it. And of course, they gotta have some quarantine references in it. Very good taste, USACO. Quarantine for the production during the outbreak. How? Yes! Dude, why is USACO so good at problem writing? God dang it. Farmer John's cows have come up with a new way to alleviate their boredom studying advanced physics. In fact, the cows have even managed to discover a new subatomic particle, which they have named the mu particle. The cows are currently running an experiment involving n of these mu particles. Wow, yo, n is less than 10 to the 5. Particle I has a spin described by two integers xi and yi in the range negative 10 to the 9 to 10 to the 9 exclusive. Sometimes two mu particles interact. This can happen when xi is less than ji and yi is less than yj. Okay. Under these conditions, it's possible that exactly one of these two particles may disappear. At any given time, at most one interaction will occur. The cows want to know the minimum number of mu particles that may be left after some arbitrary sequence of interactions. Okay. First line contains a single integer n, the initial number of mu particles, and each of them contain the rest of the mu particles. And then the smallest number of mu particles after. Okay. So the input over here gives you like, I could draw straight lines, I swear. The input gives you a little graph over here. We got our 1, 0, we got our 0, 1, we got our negative 1, 0, and we got our 0, negative 1. So when I was reading the question, the first thing I thought is like, this particle can only interact with things over here and over here, right? And then this guy can only interact with particles like in this area or in this area. So like either to the top right or the bottom left. That's basically what the condition is. So how can we use that? So like the ideal situation in this particular case is like this particle and this particle interact, so this guy gets assassinated, then these guys interact with each other, and then this guy gets assassinated, and then these guys interact, and then this guy gets assassinated, and we're left with 1. Okay, so that actually kind of seems hard, dang. Okay. Well, if you think about it this way, like every particle could get rid of all the things to the bottom left and all the things to the top right. But the thing is, like, it's not always optimal to kill everything to your bottom left at the same point, right? Because if we took this guy and we killed everything that it could possibly kill in one go, then there's no way to kill this guy over here. So that's not gonna work. What happens if let us draw like links between the ones that can kill each other. So these guys could kill each other, and then this guy and this guy could kill each other. So we basically have like this, and then like that, how's drawing lines on a drawing tablet so hard? Like that, like that, like that, like that. Okay, so these are the ways that people could kill each other. Well, basically the point is you can only delete stuff that are connected, right? So, what's the best way to delete this in order to leave something out? So we could kill this guy over here, and then we could kill, and then that deletes these two lines, and then we kill this guy, and then you go like that. So if you go on like a path from them, like you could delete this one, or you could start with this one, go to that one to delete it, then go to the next one to delete that, then go up, then go down. So if you have a cycle, right, then you could delete everything except the original point that you start from. If you just have a line that's not a cycle, then you could only delete stuff that's in between. So you could delete this one, but you can't delete both. Oh no, you could delete both. Oh well, it would be like that. Well, being connected is like transitive, okay? So like, if this guy is connected to this guy, and this guy is connected to like a different guy, actually that's not true. So then in this particular case, it would be like that. So in this case, you could start from here and you could kill these two guys. Okay, and if we put this here, then everybody connects over there. So basically, as long as you have like an edge, you could delete one of the two things on that edge. So basically, the first thing you want to delete are the leaves. Yeah, so you want to first delete the leaves, and once you delete all the leaves, eventually you'll have cycles, right? Am I thinking about this wrong? Maybe I'm thinking about this wrong. Well, okay, so usually these kind of problems you have to do a sweep line kind of thing. Why don't we try something else? Why don't if we have a guy over here? Then nobody could possibly kill this guy. Why don't we keep track of how many people could possibly kill something. Okay, so this guy could only get killed by these two, so it could get killed. Well, all of them could get killed by two guys. So let's just say we take out this guy, and then these guys both become one. These guys become one, and then we take out the ones, and then this becomes one, like that. Okay, so why don't we just did it in order of that? Well, finding those numbers would be impossible because that would take n squared time, so that's not gonna work. Or would it take n squared time? Not if we did a sweep line algorithm, no it wouldn't. Yeah, so like updating all the numbers would take way too long. Well, basically, if we use our sweep line algorithm, what we could find out is how many to the top right could kill it and how many to the bottom left can kill it. But that doesn't help, does it? Well, okay, I think the thing we have to figure out is what condition you need in order to be the one that's left. So I guess in this case, any of them could have been left because they all have 2. So that's not right. Let's see. Well, let's think about it this way. Why don't we add like a couple more here, here, and here? And then why don't we only care about the extremes, right? So this guy has the lowest y coordinate, so he could kill everything above, but only to the right. Bro, this is hard. Holy. Fine, does this work? So this guy kills all these dudes. Boom, 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 boom. And wait, this guy can literally just kill all of these guys. Well, let us see. So if you have an example, like let's say we have like this, like that. Now that's the right connected stuff, and basically this guy could just kill both of these. Is it true that for any connected thing you could kill all of them? But let's try to find an example where you can't kill all of them except one. So this would be the same thing we were in before, one that we did here. Then it's like that. Okay, I don't think you could kill everything in this case, right? Because the only thing that could kill this one is this one, so we'll kill this guy first. Oh, well yeah, it works, right? This works. So as long as it's connected, does it work? Okay. Well yeah. As long as it's connected, you could kill everything in it except one. How would it not be connected? Well, I guess if you just put something like over here, then it won't be connected. So how do we find connected stuff? Okay, so now we have an n squared algorithm. This makes sense, okay. So in an n squared algorithm, we just draw all the like edges between the things, and then once we have all the edges, we could just DFS or BFS to find connected components, and then the number of connected components is how many ones will be left. So now we have to figure out how to find the connected components quickly. So in order to be connected in the group, there has to be, how do you define connected in a bunch of vertices? We know how to speak. So you have to be able to go from one to the other, then from the other down to that. Okay, let's see what the fastest way to find all the connected. Wait, so if I put something here and it was connected like, well yeah, no matter how you connect it. Let us put a bunch of random stuff and let's just try to figure out connected components by ourselves. So we have random stuff everywhere. Let's go. You love that song, you got this. Okay, so this might be slightly too easy because this thing is all just one big boy connected component. This guy just killed everything else. And you're done. But this guy has to be in the connected component as well. So this guy is also part of the connected component. So this just ends up with this guy surviving. But how do you find the connected components? Oh, so maybe you take this, right? You find everything to the top right of it. Then you take the highest one, and then everything underneath that to the left is also in the connected component. Then you take the lowest one, and but you also have to take the rightmost one. And then everything that's to the left will also. So in order to not be in the connected component, you have to be somewhere over here. Or somewhere outside here. So I guess you could just keep doing that process until you get to the end. Oh, but then there's also like the other side. Oh, okay. So the only ones that you don't care about. So we only care about the extremes, right? So I guess for everything we could store the highest one that's to the right of it, the rightmost one that's to the top right of it, and then the same thing for the bottom. And then we could like put which ones are already done. So then if we found something else that worked, then it would increase the bound. Okay, let's think about this slightly more. Okay, I think we're getting something, okay? So what I think is that you have to be able to decompose this into like a bunch of things that kind of look like this, and then in order for it to not be part of the same thing, it has to be strictly above here. Like it has to be above here, and it has to fall somewhere out here. Oh, well, okay, so I guess we just have to break it up into squares then. Squares that do not contain each other. Oh, that makes so much more sense. Okay, so basically, if we have like a bunch of points, let's say we have like points here, we have a like point there, we have a point, and then we have a point here, basically what our algorithm needs to do is it has to divide it up, I can't speak, into squares. So like this would be one square, and we put all the extremes as the edges of the square. And then you put another square over here. Let me put this a little lower so it's less confusing. And essentially, these squares have to be so that like each square lies entirely to the top left or to the bottom right of the other square. Because all these guys are going to be connected to each other, right? This guy's connected to that guy, that guy, that guy. This guy's connected to those guys. So everybody's connected in these things. Like even for this one, this guy's connected to here. This guy's connected to that guy. This guy's connected to that guy, so like that, and then this guy, wait, no, it should be in the same square. Oh yeah, because this guy's connected to that guy as well, so these guys are all connected. So how do we find these squares? So our first square is going to have a left side on the leftmost point, because every point is going to have to be in some square. And then we start off the bottom and top of the square at that point, and then the right side we're going to keep moving. So then we go to the next guy, and we're like, wow, he should be in the same square because he's above. So we add this guy, this top guy to the square too, then we go to this guy, and he's also below the, so now the top, okay, wait, let us restart actually. This is going to be a not very fun problem to code, but we will do it, I suppose. Okay, so we have a bunch of points, so we're basically going to start from this guy. So right now, our left side of our square is over here, and our top and bottom are right here. Then we move to these guys, and we expand it upward, so now this guy is also in our square, and then basically, in order for this guy to get into our square, it has to be at the same x as a different one that's already in the square, which it is, so we also add that to our square. And then we add this guy to our square because it's within our bounds, but that didn't change our top and bottom at all. So now for this guy. So we'll keep this square going, just in case like another guy popped up here, in which case all of these guys would be in the same square, but that's not true right now. So we'll just keep our square open and we'll start a new square. Top and bottom are over here, and then we go to the next guy, and he's like not in the same, he's not on the top right or bottom left of this guy over here. So we got to add him, we can't add him to another square, we'll start another square over here. Or rectangle, rectangle is the right word for it, but anyways, then the next guy is over here, and he fits into two of our open squares though, because he's top right of this square, and he's top right of this square. So we combine these two squares, and now we have this other top, and this is our top, and then this guy doesn't change it. I mean, no, we had to take care of this guy. So this guy, oh wait, we did it in the, well no, so this guy has to equal x to one of the existing squares guys, so we could just add him to that square, and it'll be like that. Then this guy is top right of something, and then this guy's already within the square, so we just add him to the square, and we keep going. Okay, now this guy doesn't fit in our square, it's to the bottom right, so we start a new square. This guy fits into only this square, so we extend the square to fit in this guy. This guy already fits into an existing square, so we just include him. And then this guy over here, we start a new square because it doesn't fit into any square, and boom, we got our squares. One just for this guy, one for these three guys, one for these guys, and one for these guys. So now we got 4 remaining particles at the end. Okay, so basically what we got to keep track of are the upper bound and lower bound of each square we have, and which squares exist. Well, yeah, actually, yeah, you just gotta keep track of the upper and lower bounds of the existing squares. Wait, do you even need the upper bound? You only need the lower bound. Well, yeah, you only need the lower bound of the squares. Wait up, this is kind of big brain. Okay, so let's just start from the beginning. The lower bound is currently this. Then we go to the next guy. Why don't we start at the bottom this time? And we're like, okay, this guy doesn't fit into any of the current lower bounds, so we're gonna start a new lower bound. But then we go to this guy over here, and it's like, it fits into 2 of the lower bounds, so we're going to combine them all into the same thing. So now all these 3 guys are going to be the same square, and the lower bound for that square is just this lower bound over here. Then this guy already fits into this lower bound. Okay, now this guy starts a new lower bound. Epic. So then for this guy, we gotta make a new lower bound because it doesn't fit into any of our current ones. Then we go to this guy. We'll start from lowest to highest if they're equal x. And basically for this guy, we have to add another lower bound because it doesn't fit into any of the current ones. However, this guy fits into all three of these guys. So we basically combined all three of them. We get rid of this lower bound, we get rid of this lower bound, and boom, this was one lower bound over here. And then this guy just fits into this lower bound, so we continue this lower bound over here. And then for this guy, there's another lower bound, and then both of these guys fit into it. And then we add another lower bound, and now we got 4 lower bounds, and we're Gucci. Okay, let us code this up. I know that was really confusing, but I think it'll make sense once we code it, okay? Moop! That's such a good name, I like Moop. Let's F-stream this boy. Alright, read into N, read into XY. And then now we will keep a vector of our lower bound. So we'll include vector and we will have lower bound. Now the first thing we want to do is we want to sort our coordinates from smallest x coordinate to largest y coordinate, and within each same x coordinate we want to have the lowest y coordinate come first. And we could just do that by sorting the array. So we had to include hashtag algorithm first. But now that we have that, we could do sort over here, and we could do xy, comma, xy plus n. So now we'll just go in the same order that we were. We go for this one, now these have the same x, so we go to this one, then we go to this one, then we go to this one, then we go to this one. You get the idea. It's basically sorted in that order now. Dude, the coding for this isn't even that bad, I just realized. Okay, so what we're first gonna do is, wait, n is guaranteed to be greater than 1, right? Okay, so basically we're just gonna start by pushing the first one as the lower bound. So lower bounds are pushed back, and then we want the y coordinate of the first one. Okay, now we have to go through the rest of the points and do the logic that we were doing before. So we do for int I is equal to 1, I less than n, I plus plus. So I'm just going to do int x is equal to xy I dot first, just to make it easier for me to think about it. And basically, if our y coordinate is, actually our x coordinate doesn't even matter at all, because we know that we're just going in order of increasing x coordinates, so that doesn't matter. So we'll just look at our y coordinate, and basically if my y coordinate is less than all of the previous lower bounds, I'm just going to make a new lower bound. However, if it fits into any of the other lower bounds, we're going to delete all the lower bounds less than it and create a new lower bound. So first what we're going to do is we're going to figure out where it fits into our array. So do we want to do lower bound or upper bound? We probably want to do upper bound because we want to delete everything that's below it and then add in the smallest bound back again. So we're going to do upper bound, okay. So we're going to do int index is equal to, actually we can do a vector iterator. Oh wait, that's not how you do it, you gotta do it the other side. Oops, I know how to type C++. Dude, I'm too rusty, god dang it. God dang it, dude. Okay, so we basically have our iterator here, and we're going to do upper bound, and then we're going to do lower bound dot begin, lower bound dot end, and then we're going to pass in y. So basically you want to delete everything from our current location until we get to the last thing that's left. So first we had to do the case where there's nothing below it. So we had to create a new lower bound in that case. So if upper bound, or if iter is equal to lower bound dot begin, that means it's the smallest lower bound so far. In that case, then we got to make a new lower bound. And our new lower bound is going to be at the y coordinate of the current point. Otherwise, we are going to have to delete everything below it, except the last thing that's not, or the last thing that's below it. Okay, so we are going to do while iterator is not equal to lower bound dot begin. So while it's not the first thing in our array, we're going to delete everything else that's below it. So in this case, we got to keep subtracting from iter and delete it. So first we got to do iter minus minus because, let me just draw it out for you. So we got an array, right? So let's say it's 0, 1, 2, 3, and we do upper bound of 1. So it would say, hey, we could put it here. If we put it in the second index, then we would still be sorted. If we put in 1 over here, it would still be sorted, so that's good. However, the only one that we want to delete is 1. We don't want to delete the 2 because that's greater than 1. So we want to subtract 1, so it's pointing at this guy, erase this guy, and then we're good. So that's why we do iter minus minus, and now we'll start erasing stuff. So then we do lower bound dot erase, and then, is erase the right one? I'm pretty sure it's erase. And then at the very end, we just literally see out lower bound dot size. Nice. Let's test it out. So 4, 0, 1, 1, 0, negative 1, 0, 0, negative 1. Okay. Whoop. Iter minus minus, boys. Okay. Now it should work. But dang it, I keep forgetting how to do while loops, man. And 1 is correct, that is right. Let's do an example where there are more. Actually, why don't we just try it, and if it doesn't work, then we can work on that. But I think this should work. Alright, moment of truth. It's probably not gonna work, but it at least gets the first test case. Okay, that's all that matters. Yep. God dang it, what? Okay, let's test it if we do it on this kind of thing. So we'll do like, how many do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14. Okay, so we have 14, and then we have negative 4, 3, negative 3, 2, negative 3, 3. So this should give us 3. Why can't I read this? God dang it. Oh, it gave us 6? What the heck? Oh, whoops, they're not 14. I didn't do 14. It should be 9 or 11. Okay, so good. We have something that we can test, so let us see. So what it should do is, let us just draw this test case real quick. So this should have 4 different areas. Okay, but we still got 5. And then after each one, let's just print out what our lower bound array is saying it is. So we will do for int I in lower bound. Probably should do j. See out lower, or see out j, and then space, and then after that we'll see out an endo. Okay, run it. So it first has 3, then it has 3, 2, good. Or yeah, that's good. Oh, then it only has 3. Oh, whoops, I have to insert it at the bottom. Should be push or insert at 0. So we're gonna insert it at lower bounds of 0, and then comma y, and then this should work. Okay, good. This is how we want it to work, and it gives us 3, what? So it goes 3, 2, 3, 2, stays at 2. Then it goes to 0, 2, which is right. Negative 1, 0, 2, right. Oh, this one, wait a minute. What is this one? 1, comma, oh, I did 1, comma 2, so that makes sense. Okay, so it should be 3, so now it should be working. So let us take this out and try it again. Okay, second moment of truth. This is gonna be epic, I swear. Promise, come on, get more than the first kid. Hey! Let us go! Oh, that was actually so satisfying, dang. I haven't solved the USACO problem in so long, and that felt so good, god dang it. So let me just explain the logic that went into this again. So basically the first thing I noticed is like, if these like points are connected, right? Then no matter how they're connected, there's always a way in which to kill all of them except one particle. However, between the different like groupings, like between connected components, you can't delete between the two. So for every single connected component, you're gonna have one left over, so you just have to find the number of connected components. Now the thing I have a hard time explaining is like how I found the connected component. So the way I thought about it personally is like, basically anything, if we look at this point first, right? Anything to the bottom left, so anything in this area and anything in this area is going to be connected to it, right? Then, in order to find things that are connected to things that are connected to this, we had to look at the other things. So this one is going to expand it over here to everything under here and everything over here. This guy is going to expand the range to everything over here and like everything above too. But that's already covered because this whole thing is covered already by this guy over here. So now the only things that are not like contained within this connected like black dark area over here are the guys that are above the uppermost one and to the left of the leftmost one, which is over here. So that's why these guys are separate connected components. And then the same idea for everything over here. Alrighty, I hope that was helpful. That was a really fun problem to solve. I don't know why, but it just felt so satisfying. But if you guys want more of these, then let me know down in the comments. It was really fun to make this video, but I actually do have to get on my AP curriculum stuff, okay? It's almost there. I'm going to make some more review videos for that. Alright, anyways, thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching again, and see you guys next time.